Hello. So in the previous module, we took a minute and we looked at some samples of data that were not particularly good samples for one reason or another. And so the main point in this module is when we say a sample that is not particularly good, the statistician would say that is a biased sample. And so we want to talk about what exactly we mean when we say bias when talking about statistics. So our general definition is we'll say that bias is a process which results in an incorrect outcome of some type. In the last module, all the samples we looked at, they would probably yield an incorrect result or an incorrect conclusion. And so what we want to do today is we want to look at a few different types of bias that tend to occur in statistics so that you can know them by name. And the best way to do this is to look at a couple of examples. So let's take a look at some examples and some possible sources of bias. So in the first example, suppose you take a coin from your pocket and you flip it 3 times and it ends up landing heads all 3 times. So you say to yourself, the coin is supposed to land heads 50% of the time, but it actually landed heads 100% of the time in the sample. And so the subject of our story concludes that the coin is unfair, since it's landing heads more often than expected. So in this first example, I hope I don't have to try to convince you too much that flipping a coin 3 times, or simply taking a sample size of size 3, that is far too small of a sample to really make any conclusions from. And also, since we have an odd number of coin flips, it's actually downright impossible that you would get a 50-50 distribution of heads and tails, because that would mean 1.5 heads and 1.5 tails, which is impossible. But the bigger problem is, in statistics, we usually try not to make conclusions based on 3 data points, and so here the source of bias is the sample size is simply too small. And the question we will want to eventually ask, but not today, is eventually we'll want to be able to say things like how large of a sample is large enough before you can actually start making conclusions in a sample of data. And that is a pretty difficult problem, so that is something that we won't get to until we get to about chapter 8 in the book. So if you want to look ahead and see what's going on there, that will be the main question that we run into. If you want to do a little bit of review, if you start classifying the figures in the problem, the 50% figure, that is actually a parameter. That's a population figure of what should happen with the coin. And the 100% figure, that's actually a statistic, because in this case, the 100% figure came from a sample of data. So we would say that is a statistic. University has a BS in sports management and leisure, and they want to study what percentage of their graduates are able to find employment within 6 months after they graduate. So in the study, what they do is they send out 500 surveys to recent graduates of the program. 243 of them actually return the survey back, and out of that 243, 210, which equates to about 86%, they say that they were able to find a job within 6 months after they graduate. So there's a couple things wrong with this particular sample, so maybe you should take a second and pause the video and think about what a couple of problems with this particular study are as far as the way it was conducted. Now, one thing we would have to worry about pretty seriously is if you look at the data in the problem, they sent out 500 surveys, but only 243 of the surveys came back. And so I think a natural question would be, we really would have to wonder whether the people that actually sent the survey back are actually different, or they're getting different job outcomes than the people who did not return the survey. So the big question is the people who returned the survey and the people who did not return the survey. Are those two groups different? Because it seems at least possible that the people who did not return the survey, maybe their job prospects or their job outcomes weren't nearly as good as the people that did return the survey. A couple of terms you should know in statistics is another problem the way this survey was instituted is participation was totally optional. And the second problem is that the participants who actually chose to send the study back, That was a completely voluntary process. So the two things we're worried about is that the people who actually chose to send the survey back could be very different than the overall population. And in statistics, we would say there's a question or there's an issue of self-selection. So basically, people could decide on their own whether or not they wanted to be sampled as part of our survey. And anytime that happens, we always have to wonder if the people who choose to be in the study are actually very different than the people who do not choose to be in the study. And a more particular form of self-selection that's occurring in this problem is, since the subjects were under no obligation to respond to the study, we would say that this is a voluntary response sample. And again, it's a similar issue where you have to wonder if the volunteers who were willing to talk about what their job status is, whether that was a much different group than the population as a whole or the people who did not volunteer to be part of the survey. Again, if you start looking at the numbers in the problem, notice this 86% figure is a statistic, and we really would have to wonder if the actual population parameter might be much different than that. For instance, if we were to factor in the people who didn't actually return our survey. Next example, let's suppose some university, they're facing a horrendous budget cut, and so what they do is they get on the phone to 1,000 students and they decide to poll the students. And the question they ask is the question in bold here. So we ask them the question, well, since there's this looming budget crisis, would you be in favor of having your fees and tuition increased, or would you rather see us cut some programs at the university, possibly the program you're enrolled in? And at the end of the day, let's say that 68% of the students actually responded that yes, I think the fee increase is the preferable option. So the university says, hey, great news. The students are overwhelmingly in favor of us increasing their tuition and fees. So again, I hope nobody seriously believes that the students are kind of begging the university, please, please, please increase our tuition and fees. And so let's think about one big problem in the way that this study was conducted. And the biggest issue in this particular problem is if we look at the way the study was actually conducted, in particular this question, would you rather have us increase your fees or would you like to see programs at the university cut? Well, the answer to that question is almost certainly no, but the way we've actually worded the question, it's almost presented as a one or the other proposition, and almost, perhaps deliberately, perhaps not, the way this question is constructed, it's really meant to suggest or to have people say, yes, we prefer the fee increase option. And again, we don't know. Maybe this was deliberate, maybe it wasn't. But what the statistician would look at this is it's distinctly possible that whoever designed this study or this survey, maybe this was intentional, maybe it was unintentional, but we would say that the experimenter or that the observer actually had an influence on what the results of the study were. So the statistician would say there was a form of either observer bias or sometimes we would say experimenter bias in this particular problem, since the person designing the study or the survey had some impact on what the results of the study or survey ended up being. So in particular, if you're a social scientist and you will spend your days actually conducting surveys and questions, you always have to be very careful to make sure that the way you've worded the question isn't going to unwittingly sort of favor one response or the other. And again, that 68% figure, that's a statistic because that came from our sample. And again, since this is probably a very biased sample, we would have to be careful before reading too much into that particular figure. Another example, this is true data. And a study was done which found that life expectancy, or found that life expectancy in countries where you have at least one TV per two people, it's actually 10 years higher than it is where you have less than one TV per two people. And so the hero in our problem is a philanthropist, and they say, well, I guess we've probably got thousands of unwanted tube TVs sitting around in landfills or in people's houses. And so let's increase worldwide life expectancy by taking all these unwanted, old, obsolete TVs and shipping them all over the world. So again, I hope you don't seriously believe that this is a reasonable conclusion, and so maybe pause the video for a minute and think about, what's actually going on, because this data is 100% truthful. I will tell you that much. So after thinking about it for a minute, I think you reach the conclusion that just increasing the number of TVs around the world, that is not going to have the effect of actually increasing worldwide life expectancy. But if we think about the reason why there's high levels of TV ownership in countries where there's high life expectancy, well, the reasons I can think of is if there's lots of wealth and resources to go around, then probably people are going to own lots of TVs. Like in the United States of America, in my house, there are 4 TVs per person in the house. And the idea is if you have lots of wealth and resources, you probably have lots of other things too. Like, for instance, access to food and clean water. You probably have halfway decent health care. You know, I can think of 100 other things, but these are some big reasons why in countries where you have a high TV ownership, you also have a high level of life or high life expectancy. And a very important term, which you should know based on this problem, is these hidden factors that are really explaining the relationship. So we would say there is definitely a correlation between TV ownership or level of TV ownership and life expectancy. But the reason is not what it appears to be at its face. The reason is that all these hidden factors are buried in there. And so in statistics, all these hidden factors which actually explain the relationship, we would call those confounding factors. And that's a very big deal in statistics. So anytime we see a relationship between two quantities, we always want to know, is that relationship exactly what it appears to be, or are there some hidden factors or some hidden forces that we can't quite see, which are actually explaining or actually causing the relationship that are there? So whenever we say confounding in statistics, we mean the relationship is maybe not exactly what it appears to be. Next example, I was reading the newspaper one day, and there was a story in there that said when people are treated for injuries after automobile accidents, about 30% of the people needing treatment actually suffered some kind of an injury because of the seatbelt. And in the Augusta Chronicle, if you ever read the comments section, well, one of the comments in there was, well, therefore, seatbelts, I guess, are extremely dangerous. And, people shouldn't be made to wear their seatbelts. So let's make sure we understand why this is not a particularly valid line of reasoning. Now, I hope we all believe that this person, they're placing themselves in terrible danger because in this case, we're only looking at one particular subset of the population. Here, we're only focusing our attention to people who actually needed to be treated for after an accident. And almost all those people presumably were wearing their seatbelt because most everybody does wear their seatbelt these days. And the problem is, what we don't see in this problem is we're only focusing on people who actually needed like medical treatment after an accident. And presumably there are an awful lot of people who were wearing their seatbelt, and because they were wearing their seatbelt, they didn't require any medical attention whatsoever after the accident. So we always have to be careful. In this case, we're only focusing in on one subset of the population, which was the people who needed treatment after a car accident. And a term we would use in statistics when we make this mistake of only looking at one subset of a data set and ignoring sort of another group that goes along with them is we would say we've committed a form of survivorship bias. So in this problem, when we talk about who the survivors are, in this case, the survivors, the group we're actually looking at, those are the people that required medical treatment after their car accident. And the point is that group could potentially be very different than the overall population. So only focusing on the people who needed treatment after a car accident, as opposed to looking at everybody who was involved in a car accident, that's a little bit questionable reasoning. And so it's usually not a good idea to only look at one particular group versus another whenever we conduct a study. One other example, and this is a term that's not in the book, but I think it's fairly important, is suppose we've got a number of people who live near a water treatment facility, and suppose the city wants to conduct a study to see if exposure to whatever chemicals they use in the treatment process, if that causes any health problems. So in this problem, let's say we're going to have an army of researchers that are tracking these 4,000 people for life, and they're going to look at 500 different diseases that these people could possibly contract. And what it's found is these 4,000 people, they have an unusually high number of cases of Morgellons. And so what you could do here is, I don't know if you're a biologist or if you know what Morgellons is. It's kind of this weird, it might be a neurological condition where people feel like they have things growing out of their skin, and it's an extremely rare disease. But back to the problem, well, then what they conclude is maybe there's a link between this disease and the water treatment process. And this problem is a little bit more subtle as far as why we'd have to maybe be a little bit suspect of the conclusion that's reached. So again, you might want to pause the video and think about it for a few minutes. And after you come back, the big mistake we make is notice we tracked over 500 different diseases in this sample of 4,000 people. And notice we only saw, or there's only information that something weird happened in one of those 500 diseases. Nothing was said about the other 499, which maybe should give us a little bit of pause in this problem. And the cardinal sort of sin that was committed here is later on in the course, we will see that anytime you have a fairly large data set, you almost certainly expect to get one data point in there that might be considered an outlier or is just an unusual data point. And further, if you think about it, if this disease is really strange and rare, it could be that one person out of 4,000 contracting this disease, that could be an unusually high figure. So it could be we're basing a conclusion based on one person out of 4,000 contracting one disease out of 500. And when you really start thinking about it, that is probably not a good basis for making any kind of a conclusion. And so the term that we're going to illustrate here is what we did in this problem is we have a very large set of data out there. We're tracking 4,000 people in terms of 500 different diseases. And all we picked on is we basically picked on 1/500th of the data, and nothing was said about the rest of the data. And so in statistics, when we do something like this, if we focus on only a tiny fraction of the available data and you ignore the rest of it, sometimes you would call this the sharpshooter fallacy or the sharpshooter effect. And so to finish this module, if you're not quite sure why you call this the sharpshooter effect, let's kind of finish this module by looking at a picture, which may make it clear. So suppose I claim that I'm an expert target shooter, and here are the results of my expert target shooting. So I hope you say to yourself, well, I'm not much of a target shooter because of the scatter and basically the shots are all over the place. So your first observation should be, well, they don't look like an expert sort of sharpshooter to me. On the other hand, if I conveniently ignore most of the data in this data set, so let's do just that. If I ignore most of the data, well, notice now it looks like maybe I am an expert marksman or I am an expert sharpshooter. And so I think that's kind of a good, if silly, way to kind of think about what the sharpshooter effect is and why it's named that way. So if you ignore a lot of the available data, well, chances are you can find some kind of a pattern in any very large set of data. And you always have to be careful that you haven't sort of knowingly or unknowingly ignored most of the data to sort of reach a conclusion. So now you know several different sources of bias that occur in statistics, and this is not sort of comprehensive, so I would suggest make sure you've read chapter 1 of the book. They talk about some other ones in there, but for now, that's kind of a quick overview of some of the main sources of bias.